Okay, so this next video is called Analyzing Polynomial Functions. The unit that we're in pre-calculus is all about polynomial functions. So we've spent a significant amount of time the past couple of weeks sketching polynomials. We've factored polynomials, we've found roots, we've built equations of polynomials given different information, and now we're at the part where we're going to do some application problems. The problem that I'm going to go over is very calculator active. So if you don't have your graphing calculator handy right now, I recommend that you hit pause and go get it. The calculator that I will be modeling is with the TI Inspire. So I'll be solving all steps of this problem on the TI Inspire. If you don't have an Inspire, don't worry. I'm sure your calculator does all the same things that the Inspire does. It'll just do it a little bit differently. So let's get started with this. This problem comes from a textbook, not one that we use in this course, but a textbook that I like to refer to. We've got a cardboard box with a square base. Each edge of the base has a length of x inches as shown in the figure below. So this is the base over here. You can't quite see that side. So this is x, that's x, that's x, and that's x. All four sides of that base are going to be x. The total length of all 12 edges of the box is 144. So since we have a square base, we've got x, 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 and x. That is also going to be the length of the top. And then we also have the four sides. This one in the back is invisible, or at least it's invisible from our perspective. So we have x, 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 and x. And I'm going to represent the heights as h, 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 and h. We are being asked to show in part A that the volume of the box is given by the function v of x equals 2x squared times 18 minus x. Then in part B, we're going to be asked to find an appropriate domain for this function. In part C, we're going to be asked to find on what intervals is the graph of v increasing. In part D, we're going to determine the average rate of change of the volume on the interval 13.2, 14.5, and then using appropriate units, explain the meaning of the answer in the context of the situation. In part E, we'll be asked to find all values of x that satisfy the inequality v of x is less than 800. And then finally, we're going to determine the dimensions of the box, which generate the box with the largest volume. These are all pretty typical questions to ask in an application question. So let's just jump right on in. I'm going to try to jump back and forth between you're seeing my handwriting on this document and then modeling on the graphing calculator. So it might be a little bit choppy in places, but we're going to do the best that we can. So part A, we're going to show that the volume of the box is given by v of x equals 2x squared times 18 minus x. We were told already that the base is a square and the length of each side is x. And again, I'm going to draw in that side that you can't see from our perspective and the base. That's x and that's x. The top is a square. All of those are x. And I'm going to call the heights, those four are h. So we know the total length of all 12 edges is 144. So if that's true, then x plus x plus x plus x plus these four x's, I'm up to 8x, plus the 1, 2, 3, 4 heights has to equal 144 inches. Since my volume is a function of x, meaning that x is the only variable in there, what I'm going to do is I'm going to use this, I like to call this my constraint equation. This constraint equation establishes a relationship between the height and the length of the base. I'm going to use this constraint to rewrite the volume formula this way. So we're going to solve this for h. We get 4h is equal to 144 minus 8x. If I divide everything through by 4h, 144 divided by 4 is 36. minus 2x. The height of the box is equal to 36 minus 2x. How do we find the volume? The volume is length, that's x, times width, that's x, times height, well, that's 36 minus 2x. That is almost exactly what we were given. Well, let's see, what else can we do? I have 36 minus 2x. There's a common factor of a 2, so I'll remove the 18 minus x, and we're going to get 2x squared times 18 minus x. That's my volume equation. So that completes part A. Now that we've established that this is the volume formula, we can use that for all the remaining parts. Let's move on to part B. In part B, we're asked to find an appropriate domain for the box. So we were told that the volume can be given by 2x squared times 18 minus x. Well, let's talk about the domain here. The domain, we're talking about all the possible inputs, all the possible x values. Okay. Since we are talking about a real-life problem, the x represents the length of the base of the box. Since this is a geometry problem, it doesn't make any sense to have a negative value for x. So the x value has to at least be greater than or equal to 0. Depending on your perspective, depending on what your pre-calculus teacher tells you, some might even be stricter with this and say that x has to be strictly greater than 0, because if x is equal to 0, then the base length is equal to 0, therefore you don't have a box. Either of these is generally going to be accepted at yes on the trimester exams and the unit tests. So that, what we've established, is a lower limit for the x. X cannot be anything less than 0. Well, let's see if there's a maximum value. Let's see. Our volume is 2x squared times 18 minus x. No matter what x is, I square it, I'm going to get a positive. That doesn't seem to be a problem. Over here, this factor, the 18 minus x, we need to make sure that this remains positive. Otherwise, we're going to get a volume that has a negative value. So we need 18 minus x to be greater than or equal to 0. If I solve that inequality, we'll get that negative x is greater than or equal to negative 18. Divide everything by negative 1. X is less than or equal to 18. That gives me a domain. I'm going to use brackets, so we're going to include the 0 and the 18. A domain of 0 to 18. Depending on your teacher, they might say that the domain is the open interval, 0 to 18. Here I'm using interval notation in both cases. If you would prefer to write it as an inequality, you could write the first one as 0 less than or equal to x less than or equal to 18. You could write the second one as 0 less than x less than 18. Any one of these 1, 2, 3, 4 answers would be perfectly acceptable as the domain answer in part B. Part C, we want to determine on what interval the graph of v will be increasing. Well, in order to figure out where v is increasing, what I want to do is I want to generate a graph. And this is where we're going to pause for a moment to come up with the to look at the graph. So let's switch over to the calculator. Alright, so I am going to put in my function. So we're going to enter the function. The function was 2x squared, parentheses 18 minus x. I'm going to hit enter. And that is what my calculator gives me for the graph. Now, we're going to have some scale issues. We're going to have to play around with the window. Since we've already established that the domain has to go from 0 to 18, what I'm going to do is go over to the window, change my window settings. For the x-min, I'm going to go a little bit less than 0. So I'm going to set -2. For my x-max, I'm going to go a little bit past 18, so I'm going to say 20. Now for y-min and y-max, I don't really know what's going to be an appropriate window, so for now I'm just going to hit OK and see what happens. Alright, I see part of the graph over here. I see part over here. I can infer from what I'm seeing here that the graph seems to be increasing, and then it's going to come back down over here. So we're missing a lot of the graph up above. So let's go back to the window. Let's change our window settings. I want to see more of what's on top of the graph, so let's change the y-max, maybe to 100. It's a little bit better. I'm still missing a lot of the graph over here. So menu, window zoom, window settings. Now I did this problem earlier, so I know that a window of about 2000 for the y-max is going to get me a very nice graph. But the first time I did this, I had to play around for a little bit. But for the purposes of what we're doing, I wanted to jump to that. Now, where is this graph increasing? The graph is increasing from right down here at the low point to right up here at the high point. In order to find that value, this value over here, I'm going to go to Menu, Analyze the Graph, select Minimum. The calculator asks for a lower bound. I know I'm looking over here for the lower bound, so for the minimum. So I go slightly to the left, select Enter. It asks for an upper bound, select Enter. And the point is over here at 0, 0. Okay, so that's where the function starts to increase. Now it continues to increase until we get to this highest point over here. We like to call that the max. So we're going to do Menu, Analyze the Graph, Maximum, same set of commands. Go to the left, go to the right. The maximum value is over here at 12. So we have 0 as the minimum value. We have 12 as the maximum value. I'm going to switch back to the other screen. Based on our graph, V is increasing on the interval 0, +12. And another acceptable answer would be to say that the function is increasing on the open interval 0 to 12. And this comes from sort of a calculus issue. The question is v of x increasing at 12? It depends. Some calculus authors will say it is not increasing at that maximum point, and then it's not increasing at the minimum point. Others say that it is. Some say that it's not. End of the story for us in pre-calculus. Both intervals are perfectly acceptable. All right. Let's move on to Part D. Part D. We want to determine the average rate of change of the volume on the interval 13.2 to 14.5. And then using appropriate units, we want to explain the meaning of your answer. Well, I know, and I would expect everybody in pre-calculus knows, that average rate of change just means slope. The way that we found average rate of change is it's always the change in the y value, so y2 minus y1, over x2 minus x1. Specifically, in this case, our x values are the 13.2 and the 14.5. So we'll have 14.5 minus 13.2 in my denominator. The corresponding y values are found by evaluating the original function at 14.5, subtracting from that the original volume evaluated at 13.2, and the numerical value to this expression